Hi again, everyone. Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to answer the question, when do fractional differential equations have special kinds of solutions that are bounded by a Mittag-Leffler function? Now, this presentation forms part of a new research paper that I'm about to publish, and I'm trying to make this particular presentation at a level that's suitable for undergraduates. So I'm going to discuss the problem, I'm going to present the main result, and then I'll give a basic example. Okay, so let me share my screen with you and we can get down to business. All right, when do fractional differential equations have solutions that are bounded by the Mittag-Leffler function? Now, first of all, you may have not have heard of a fractional differential equation or the Mittag-Leffler function, but we will discuss those things as we go through. Okay, so this is the main question that we are going to answer here. In particular, we've got some sort of differential equation, and we're looking for solutions that have a solution domain on the half line, and they're also bounded by this special type of function called a Mittag-Leffler function. Okay, so why would you want to do that? Well, there's lots of interesting answers to that question. Firstly, the Mittag-Leffler function plays kind of a similar role as an exponential function does in regular calculus. And in this presentation, we're going to look at nonlinear equations. So what happens in this nonlinear case? All right, the ideas we're going to use involve so-called fixed point methods. Again, I'll tell you what that means. And the outcome is going to be a deeper understanding of the geometric behavior of solutions, in addition to advancing our understanding or knowledge of when these kinds of problems actually have a solution. Okay, so that's sort of the why you'd want to do this. Okay, let's have a look at the problem under consideration. All right, so here is an initial value problem. Now, you would see initial value problems in a second course in calculus, or maybe in definitely in a first course in differential equations. But this one's a bit of a strange one. It has got an order which is positive, but not necessarily a whole number. So this then is a differential equation where the order could be a fraction. It could be a half, or 4 on 3, or something like that. Something that's not necessarily a whole number. Okay, and this is the idea behind fractional differential equations. You have some sort of fractional derivative, and you couple it with a right-hand side, and then you form some sort of equation. Okay, here in the second line we have initial conditions. Okay, and note here that these are regular derivatives here. Okay, now a researcher called Caputo thought that these types of derivatives here actually had more physical significance when modeling certain phenomena. Okay, all right, a little bit of housekeeping. Q is just this, this sort of ceiling Q is the integer such that this is satisfied. So for example, if Q was a half up there, then ceiling Q would be 1. dq is the fractional differentiation operator. Now if Q equals 1, then dq is just something like this, the regular derivative that you would see from calculus. This function is the Maclaurin polynomial of x of this order, and the AIs are just constants. Okay, let me just move that over a bit. Okay, so that is our initial value problem, and the f on the right-hand side could be non-linear. Okay, so it isn't like it's a standard sort of linear problem. Okay, so this is our problem that we're going to look at. It's very general, and to understand some of this, we'll just introduce a little bit of notation. Okay, so let's move on to the next. Okay, so what is this magical fractional derivative? Well, I'm glad you asked. Let's have a look. The Riemann-Liouville fractional derivative of, actually, I don't have the integral there. Let's just talk about just the derivative. Is this expression here? Okay. Firstly, you can see that you involve a regular derivative and an integral, and you've got this sort of kernel here. Here, this is the classical gamma function down here, and if, for example, q is an integer, then these things all sort of cancel out, and you can use the fundamental theorem of calculus to form just the regular derivative. Okay. And sometimes, I showed you on the right-hand side back here, this problem here with the x minus the Taylor polynomial. Sometimes this left-hand side is the notation is reduced down to this sort of c dqy of whatever, where this is this, okay? Sometimes called the Caputo derivative. Okay, and sometimes used in the literature. Okay. Now, I mentioned this Mittag-Leffler function before. Now, some of you may have heard of Mittag-Leffler. Mittag-Leffler was a very famous Swedish mathematician, and he came up with the following function. Actually, before I show you that, let's show you Mittag-Leffler. Here's Mittag-Leffler. This is probably taken around the early, perhaps the early 20th century. He was a Swedish mathematician, very, very famous. Okay, so what is this Mittag-Leffler function? All right, let Q be positive, and consider this so-called Mittag-Leffler function. Okay, so again, you've got some sort of infinite sum here, or infinite series. You've got the gamma function Q, you're summing over the K. Now, this might look a little bit familiar to you. If Q equals 1 here, what does this boil down to? Well, it boils down to the exponential function. So the exponential function that we know from calculus, regular calculus, is a special case of this Mittag-Leffler function. Okay, now we're going to be interested in the following particular form where we just replace z with this, where beta's a constant. That particular form of the Mittag-Leffler function is going to be very useful. We'll come back to that. And like I said before, the Mittag-Leffler function is kind of like a exponential function when you talk about comparing classical calculus with fractional calculus. And like I said before, for the special case Q equals 1, this becomes the special, well-known exponential function. All right, now we're almost there. I haven't got to the main result yet. I'm trying to move as quick as I can. We've got to look through, got to go through a little bit of metric space theory, and then we'll get through to the main result. Oh, by the way, I will post this. I will post this this paper, a link to the paper when it's published. Okay. All right. So I'm going to talk about a solution to our problem. What do we mean by a solution to this problem? Say on the half line. Okay, that's a good question. Well, the way I'm going to talk about it in this definition, I'm going to talk about a ML bounded solution, a Mittag-Leffler bounded solution. Okay, so basically it's a solution to this problem. I is going to be the half line. And so basically, this side has to exist on the half line, this side has to exist on the half line. They have to be equal, and all these initial conditions have to be satisfied. So this is the standard kind of thing. But I'm going to add an extra condition on that solution. This is like if you like, a geometric extra condition that we're going to look for. This supremum of the solution divided by this particular Mittag-Leffler function has to be finite for where beta is some positive constant. Okay, so what that means is, right, in our situation, I is going to be this. It means that there's some positive k. If we have an ML-bounded solution, there's some to this problem. There's some positive number k such that solutions satisfy this sort of inequality, this sort of bound. Okay, so what does that do? Well, it provides a growth estimate and insight into the long-term behavior of solutions. All right. So when I talk about these ML-bounded solutions, I mean, okay, they really are a solution to the initial value problem that we looked at the beginning, but they also have some sort of extra geometric element to them. Okay. All right. Now we are going to set this analysis in the context of a so-called metric space. Now, metric spaces are absolutely awesome. I love them. They basically just combine a set with a way of measuring distance between points in that set. Okay, so this set here is going to play a very important role because it's going to actually play the sort of set of solutions to our that relate to our original problem. Okay, so let's consider the following set. Suppose x is a function that's continuous and real valued on this half line, plus it satisfies this sort of supremum condition. Okay. Now, if we take that set and we use this d sub beta function for measuring distance, again using a supremum, notice that we're dividing by this special exponential function here. Then basically you've got a set and you've got a way of measuring distance between points in that set. Now, why would you want to measure distance? Well, it gives you a sense of convergence, and that's going to be really important in our analysis. All right, so this is an important set. This is going to be a way of measuring distance called a metric between two functions in this space. And in the paper, and I'm not going to do it now, but in the paper, I've proved that for each positive constant beta, this so-called functional or distance function really does satisfy all the properties of what's known as a metric. And when you couple this with this, you get a metric space that is complete. Now, I don't want to talk about that too much. Basically, a complete metric space just has special types of sequences in it called Cauchy sequences that converge to an element in the space. And that the limit of those, under certain conditions, the limit of those sequences are your solution to your problem. Okay? Okay. All right. Last thing before I get to the main result. The following theorem, which we are going to rely on, is known as Banach's fixed point theorem. It's a very famous theorem in mathematics due to the Polish mathematician Stefan Banach, formed about, I think, in the 1920s, I think around 1922. So let a set X and a metric D, the pair of these, be a complete metric space, and let some operator map the set big X back into itself. If there is a constant between 0 and 1 such that this inequality holds for all points in the set big X, so this is like a contraction condition. Under that condition, the problem f of x equals x has one and only one solution lying in that set big X. Okay. Now, again, I don't want to get bogged down too much on this, but this is a really famous and important theorem. Okay. So what we're going to be interested in now is trying to apply that theorem to our special case. So let's look at the main result now, and the main research in this in this presentation. Okay. Oh, actually, just before we get to that, a little bit of housekeeping. Sorry, I've jumped the gun a little bit there. A little bit of housekeeping. This function here is the unique solution to this simple linear type initial value problem, and that's sort of contained in this lemma here. So if you have this integral here, then it's basically just this. All right, just using sort of fundamental theorem of calculus. Okay, we're ready. The main theorem of this presentation. So this is the main theorem that you can find in the paper when I'll post a link. All right, so now we can answer the question: when are solutions to my original problem, when does this have a solution, and when are the solutions bounded by this Mittag-Leffler function on the half line? Okay, so here it is. Okay, it's quite a long theorem. So let me just break it down. It's a little bit abstract on a first viewing. All right. So suppose f is the f here, right? The f in the right-hand side of the problem. Okay, this f here. It's defined on the half line for the t variable and the whole real line for the x variable. And suppose it's real valued and continuous. Suppose that there is a positive constant L such that f satisfies this sort of inequality for all pairs of points in this set. This is known as a Lipschitz condition. Okay, it's a very, very famous kind of condition. Okay, so we're assuming that f satisfies that. If there's a constant that gamma that's greater than 1, such that this supremum is finite, okay, we'll call whatever that supremum is little m, then the original nonlinear initial value problem with fractional derivatives has a unique solution, one and only one solution, on the half line that is ML bounded. It's bounded by some Mittag-Leffler function. Okay, now let's just have a look at 7 for a second. It's pretty easy to see if f of say s or f of t 0 equals 0, then this thing is 0, so the whole thing's got to be 0. So that's one way to ensure that 7 holds. Okay, that won't always be the case, but that's one way of doing it. Okay. All right. So that is the theorem. So let's try to prove it. Now the proof is just basically trying to apply this Banach's fixed point theorem. Okay. So I'll just run you through that, and then I'll just give you a basic example and some remarks. Okay. Okay, all right, so that's the main result. Here is the proof. So the basic idea is to take Banach's fixed point theorem and apply it to some operator big F in some complete metric space. Okay, all right. So first of all, we're just going to introduce this kind of notation that beta is going to be L times gamma. So the gamma comes from this thing here, and the L comes from this thing here, and we'll just let the product be beta. Now we know that this pair forms a complete metric space from the previous slides. Now what we do with all these kinds of problems is we don't actually look at the initial value problem. We transform them into integral equations. Okay, and there's a famous quote by a French mathematician called Codognieux. He says there are no differential equations, there are only integral equations, because the analysis most often turns to an integral equation. So what's the integral equation in this setting? Here it is. Okay, so this integral equation and this initial value problem, they're one and the same equation. They're equivalent. In other words, if there's a solution to this problem, then it'll be a solution to this problem. And if there's a solution to this problem, it'll be a solution to this problem. Okay? Now, we like integral equations because they're more tractable, they're easier to deal with than differential equations. All right. Now, I'm going to take this and sort of add a little bit to it and take a little bit away. Now, you'll see why I've done that in a minute, and I've defined this new operator. Okay, so this big F is going to be the particular F that we're going to try to apply Banach's theorem to. All right, now you go, why have you done that, Chris? Well, it'll become clear in a minute. All right, so this then is going to be your grand operator big F, and we're going to try to show that F maps this set back into itself and is some sort of, and satisfies some sort of contraction condition. All right, if we can do that, then we know that we can apply Banach's fixed point theorem, and F will have a fixed point, so this equation will hold, and that means the original equation will hold. All right, so showing that big F has a fixed point is equivalent to showing that 8 has a solution. There's 8. And in turn, that's equivalent to showing that the original problem has a solution. All right, so the first thing we're going to try to do here is to show that F maps this set back into itself. Okay. So how do we do that? Well, let's start with a function in that set and show that the image of that function, big F of x, is going to be in that set as well. Okay, so let's start with x in that set, and we want to show that this thing's finite. Okay, and the other thing is we want to show that big F of x is continuous. But let's do this first. So we look at this, we've got that. Now, we know from the assumption in our theorem that if I sort of take absolutes there and absolutes there, that is going to be less than or equal to m, because that's an assumption in our theorem. Okay, and I know I can take this out because of the Lipschitz condition. Again, that's another assumption in our theorem. Okay, let me see if I can find that. Okay, so that m is there. Okay, that's great. And this thing, we know that that's true too. So the v will be just 0 here, right? So that becomes there. So that's from our assumptions in our theorem. And what I've done then, I've taken the m to the other side just to save a bit of space on this left-hand side. And we'll get this minus this, which is this. Now, you can see what's happened. I've inserted a Mittag-Leffler function down there and up there. So there and there. Then what I've done is I've said, all right, let's take the supremum of that outside with an inequality, okay? And then look at the supremum of what's left. Now I can integrate what's left over just through that lemma, and I get this. And then I just need to take the supremum of what's left. So that'll divide into that, and that'll divide into that. Here you'll end up with L on B will be 1 on gamma. Now this is already finite, right? And I know gamma is greater than 1. So this combination is finite, right? So what we've done now is we've shown that for every function x in C sub beta, big F of x is also in C sub beta. Well, not quite. I haven't shown the continuity, but those inequalities guarantee that the finiteness is maintained. Okay. Furthermore, I'm not going to do this because it's a bit, it takes at least another couple of pages. Furthermore, f of x, big F of x is continuous on this set. So what that means is that f maps C sub beta into C sub beta. Yes, so we're happy about that. All right. So in other words, we have just ticked off this condition, right? We know that, we know that. Now we just got to show it's a contraction, and then we're finished. So let's do it let's show that it really is a contractive map with respect to this way of measuring the distance. Okay, we claim this is going to be the contraction constant. So let's consider x and y in this set, and then we're going to consider this distance just like we would over here, except we've got a beta. All right, so that's it there. Now, writing it out in terms of the integral, you'll get this. Now, this little f satisfies a Lipschitz condition. All right, so I can go from there to there, keeping the inequality. And then what? Well, I can again, and you'll see this trick again here, insert a Mittag-Leffler function down there and up there, and then I'm going to take this out. I'm going to sup that up, and I'm going to take that out, and this with a supremum becomes that under the inequality sign, and I'm left with that. Now I know what this is. The lemma before told me that I can just integrate this to get this, take the supremum again, and I'm left with this. So we end up with an inequality like that. Okay. Now gamma is assumed to be greater than 1, right? We've assumed that. So this shows that big F is a contraction mapping. It shows that for alpha equals 1 on gamma, this is true. So we've satisfied all the conditions of Banach's theorem. Hooray, we did it. Okay, it took us a while, but we did it. Okay, so what does that mean? It means that big F has a unique fixed point, and that then will go on and solve the original initial value problem. So let's just clean up. Okay, so we see that we invoke theorem 3. There's a solution in this space to this equation here, and this x in turn is a solution to our initial value problem. All right, so you may be thinking now, well, come on, Chris, this Lipschitz condition, when does that hold? It's pretty easy to check that, but when does that hold? Well, if f is, say, continuous and its partial derivatives are bounded on this sort of half line crossed with the real line for some constant k, then inequality 6 will hold with Lipschitz constant L equal to this bound. Okay. All right, should we do an example? Let's do an example, just a quick one. All right, suppose you have the initial value problem at the start with this is your right-hand side. Well, f's obviously continuous everywhere, and df dt, df du, I beg your pardon, df du. If I differentiate this, I get 1 on 1 plus t squared. If I differentiate sine, I get cosine. And this will be bounded by 1, and this will be bounded by 1, so that would be your Lipschitz constant. Okay, this satisfies all the conditions of our theorem, and therefore this subject to this as the right-hand side of your differential equation with some appropriate initial conditions has one and only one ML bounded solution. So that's just a really simple one. Okay, and like I said at the start, I just wanted to end with a remark regarding the ML boundedness. The main theorem, theorem 5, tells us a few things. It tells us that the problem has a solution, and there's only one and only one solution, and the solution's ML bounded, or has, I guess, sort of bringing that all together, you would say it has one and only one ML bounded solution on this interval. Okay, and this tells us information about the long-term growth behavior of the solution in the sense that there's a positive constant x, such that x is bounded by this, a constant times a Mittag-Leffler function. Phew, okay, so what did you think? There's a lot going on there, but I hope I've given you a little bit of a taste for research there. If you haven't seen metric spaces before, that's okay. I've got some introductory videos on that on my YouTube channel, and I'll be putting up a link to the paper when it's published. So if you have any questions, any comments, I'd love to hear about the research that you're doing, or if you're interested in any forms of research, you can just post them in the comments section. Thanks for watching, everybody. I look forward to seeing you again and hearing your comments. Bye.